thank you very much. Thank you for the kind invitation for organizing this, and also thank you for staying here until the very last moment. I will try to be brief. So I'm going to say a few words about these few projects I've done in collaboration with Pratik and Migni. All of us overlapped at Oxford. Now we scattered away, and also with Timo Weigand more recently, plus ongoing work. So before going to the real part of the talk, I want to show you this slide, which I believe summarizes the things that I want to say here today. So I'm going to be very optimistic. So let's assume that we find an axion tomorrow, and by this I mean a point in this parameter space, this cartoon of the coupling to photons versus the axion mass. And of course, with this bit of information, we can start asking the usual questions, which are of course very interesting, like is this guy dark matter or is the QCD axion? The main message of this talk is, many of you have already worked on similar stuff, which is that axions are uniquely sensitive to UV physics. And in particular, the provocative statement in some sense is that if we find a light axion coupled to photons, by light I will specify what I mean by light later, we can rule out some well-motivated UV completions of the standard model. In particular, I'm going to be discussing why we can rule out or test, if you wish, four-dimensional GUTs, also higher dimensional GUTs like the so-called orbifold GUTs. Also some nice string theories like the perturbative heterotic string, and also F-theory GUTs if I have time, but this is work in progress, so I will just show one final slide if I have time. Good. So an example of a light axion that can give us all this information about the phi UV is, for example, an axion that generates something called cosmic birefringence. So let's assume that we have an axion coupled to photons via this kind of term that you know very well, and that this axion has a mass between the Hubble parameter today, 10 to the minus 33 electron volts, and the Hubble parameter at CMB, around 10 to the minus 28 electron volts. As this field rolls down after CMB from the point where it was frozen to the minimum, if this axion has this kind of coupling, it will induce the rotation of CMB photon polarization by this angle. This angle is calculable. It depends just on the field range that the axion rolled, the anomaly coefficient times the gauge coupling of electromagnetism. So the exciting part is that there is currently some, I will just call it hint, I will not call it anomaly or evidence. There is a hint for non-zero beta that comes from the reanalysis of Planck data by this group led by Komatsu, and also confirmed in a later reanalysis. If this turns out to be true, do
you know something about how much we can improve this?
I think we will find out soonish. I'm not involved in any of these collaborations, but I think the Simons Observatory can tell us about this. Soonish, I don't know what's the timeline, but I think it's happening or will happen soon.
Are there others, physics that can lead to this angle?
Could be systematics like dust.
Okay.
New physics, I think it's hard to explain this kind of parity violating, quote, quote, effect without relying on something like an axion. As far as I know, there is no other, let's say, good BSM physics explanation. Yeah. Okay.
This is like coming from like some universal axion field, right? The uniform axion field or something. It's not like a sourced by some axion strings. Right? There's a
axion strings can also generate this,
but that will be somewhat different from.
I think it's different. I don't remember from the top of my mind.
So also look for cosmic strings.
Yes. Pratik has a paper about this, and there are others. I think. I think the angle is different. I'm not sure. I will just
they are more localized. Maybe.
Yes, and yeah. I will just take it as, so this is the kind of signals, if you want, that can tell us a lot about these kind of theories that I will now be telling you why this is the case. Okay, so I think it's 2026, so everyone is more or less familiar with axion physics, but I will just very quickly review what I mean by axion here. It's not going to be necessarily the QCD axion. For me, an axion is just going to be a periodic or compact scalar field with this kind of shift symmetry that, as you know, is broken by effects like instantons and similar effects. Phenomenologically, this shift symmetry is very important because it totally shapes the kind of interactions that we can have, like this kind of derivative couplings to fermions, these topological interactions with gauge bosons, and also periodic potentials. In the context of field-theoretic axion models, the axion is typically understood as a pseudo-Nambu-Goldstone boson of possibly anomalous global symmetries, like the case of the Pechequin symmetry, which, as we saw earlier today, when you break spontaneously, you can get an axion that couples to QCD and solves the strong CP problem, and all this information is fully encoded in this bit of in this quantity, the anomaly coefficient for the mixed anomaly with QCD of this global symmetry. Okay, so generic motivation, as I said, appear in many BSN constructions as well as in the low energy limit of some string compactifications, solves the strong CP problem. That is the case of the QCD axion where you promote theta, the theta term of QCD, to a dynamical variable. You realize that this field gets a potential from QCD, and the minimum, assuming there are no other contributions, turns out to be CP conserving, so you drive dynamically the theory to a CP conserving vacuum and you solve the strong CP problem. Now, experimentally or phenomenologically, this model is really amazing because it's almost a one-parameter model. Once you fix Fa, the decay constant, most of the important relevant quantities are fixed, like the axion mass. This is extremely important for the experiment. And also in order of magnitude, the expected interactions with the standard model degrees of freedom are also fixed. This was generic motivation for axions. For me, an axion is going to be, in the context of this talk, is going to be interesting because of this kind of quantized couplings that they have with gauge bosons, as you all know very well. What I mean by quantized, I don't need to emphasize this a lot to this audience, but what I mean is that the gauge coupling of electromagnetism runs. The decay constant is also a dynamical quantity that depends on the energy scale. And on the other hand, this curly A is just the anomaly coefficient, and it's just an integer. So this means that once you fix it in the UV, you can use anomaly matching arguments to argue that it remains constant in the IR, as we have seen in many talks during this workshop, this one or related quantities. And yeah, there is this nice analogy which to this audience I don't need to justify, but the fact that the Fa, the decay constant, depends on the energy scale, but the anomaly coefficient is not affected by renormalization is nicely explained by the analogy with electromagnetism, where we understand the photon as a one-form gauge field, and we see that alpha depends on the energy scale. It runs logarithmically, as you all know, but the electron has an integer electric charge, and this is independent of the energy scale. So this is just going to be the main idea of the talk. I'm going to be using the axion photon coupling as the best channel to access UV physics, that is physics at the Guth scale, at the string scale, which is otherwise inaccessible to other experiments. That's going to be the idea. And yeah, let me also mention that there are many recent papers that use this quantization of anomaly coefficients to infer things about the UV. And as we saw earlier today, in 2023, there was this paper burst when these 3 or 4 papers appeared at more or less at the same time. Some authors are still here in the audience.
Can I ask one question?
Yes.
So we also know that the axion can mix with other axion-like particles, like it mixes with the pion.
Mm-hmm. That spoils everything in general. So every statement
is, in the IR, that coefficient it doesn't appear to be.
Yeah. Every statement that you can make about quantization is generically going to be spoiled by the mixing with other particles. But I'm going to argue that for light axions coupled to photons, mixing is not going to be relevant. I will come to that later.
Just to answer, when you will talk about axions, will you have in mind QCD axions?
No.
So only axion-like particles?
No. Any axion for me is just going to be this kind of particle with this, with the shift symmetry that couples to gauge bosons.
I just want to understand, do you assume that the coupling with gluons is not there? Or
No, if in 5 or 10 minutes it's not clear, we come back to this, but I'm going to answer this question soon. Good. So as a phenomenologist, to me, one of the most exciting parts of axions in general is the huge experimental program that there is trying to find this particle. We have, so if we focus, this is, I forgot, this is from Chiara and O'Hare. If we focus on the experiments in green here, we see many ongoing and planned experiments throughout the world. And there is also huge diversity in different experiments. Like, for example, we have axion alloscopes, which are resonant cavities, electromagnetic cavities that essentially scan in the frequency of the cavity in order to match the axion mass, and then you get a peak in the signal. That's how you search for axion dark matter. Light shining through a wall, which is essentially you take a very strong magnetic field, you put a wall in the middle, and then you shine a laser. And because of the effect of the magnetic field, there is a non-zero probability that the photon oscillates into an axion. It goes through the wall, and then you detect it at the other side of the wall. And then there are also helioscopes, like, for example, CAST, that was at CERN, which essentially took one of the dipoles of LHC. They recycled the dipole to just point it to the sun and try to convert axions which are produced by the sun into photons. More precisely, for axion-photon coupling, we have, now this is a real plot with real constraints, GA gamma here in GeV inverse, axion mass in electron volts, and we have a very busy plot, but there are three important features. The first one is that solid colors are already excluded by all these experiments that you see, for example, CAST, as I said, or alloscopes here mainly is an experiment in the US, ADMX. Second important feature, there is a very nice benchmark, which is the QCD axion, which we all like, which is where essentially this quantity, the coupling to mass ratio, is fixed by very well-known quantities, like the decay constant and the mass of the pion, up to a very mild model dependence. E over n is just the ratio between anomaly coefficients of the PQ symmetry with electromagnetism and with QCD, so there is a mild model dependence. And because of this, this prediction is just a thin band and not just a line. And final feature is that there is a huge new region to be explored. This is this region in blue diced line, where you see this name, alloscopes future, hopefully near future, where we will cover a new, huge new region of parameter space, also hopefully touching or reaching the QCD axion prediction. But as you see, most of the bulk of the new region is to the left of the band, and this is also going to be important for later. Okay, so I said I want to be very optimistic. So let's assume that we discover a point in this parameter space, and the goal of the talk, as I said, is what can we learn about the far UV. The first thing I promised is that we can learn about unification. And just to be clear, what I mean by unification is that I take the 3-to-1 of the standard model, QCD and the electroweak sector, and I embed it at very high energies, at what I call the GAT scale, into a simple gauge group. For me, a simple gauge group is going to be something like SU5, something like SO10, E6, your favorite group. The results are not going to depend on which is the group. The results are also not going to depend on what is the symmetry breaking scale or the symmetry breaking pattern into 3-to-1. It will just depend on this assumption, which is a strong assumption if you want, or is a reasonable assumption if you like GATs, which is that all the generators of the standard model come from the same non-abelian group. That's the only assumption I'm going to make. And yeah, before moving on, let me just remind you the motivation for GATs. We saw a related discussion by Seth earlier today. I think it's fair to say that GATs are the best explanation that we have, or the best answer that we have to this question, which is why is the hydrogen atom neutral, at least with this precision. Second, a little bit more subtle, is that we know that the standard model is a chiral gauge theory where gauge anomalies cancel. This is a non-trivial statement which is very nicely explained by theories like SO10 or E6, which are always anomaly-free, but still they allow for complex or chiral representations. And finally, more phenomenologically motivated predictions like the unification of couplings at very high scales, a closely related one which is the weak mixing angle prediction at low scales, and some fermion mass relations like the mass of the boson and the mass of the tau. This ratio is nicely predicted by GUTS. I can tell this is a theory-oriented audience because no one asked about the first and second family, which is a disaster. But this is, I'm just showing the nice features. Okay. So what we have done, as I said, is that we have used the fact that axion couplings to gauge bosons are quantized. That is, we have used anomaly matching arguments together with gauge invariance of the theory at the highest energies when this phase G gut is unbroken, in order to obtain very strong constraints for the axion photon coupling that I'm going to show you now. And just let me remind you that these arguments are based on topology, so they are completely independent of what is the gut scale, first of all, the symmetry breaking pattern, or any physics between the electroweak scale and the gut scale. So in more detail, the starting point is this one. We have a generic gut gauge group, which I'm calling here G gut. It can be SU5, SO10, whatever, times a bunch of commuting global symmetries, U1, PQ, I, which we can break spontaneously. We obtain axions from, or more precisely, Goldstone bosons from this symmetry. And depending on the fermion charge assignments, you could think that some of these symmetries have a mixed anomaly with G gut. But at this point, you should stop. You should think about a similar situation in the case of the standard model, where baryon number and lepton number both have a mixed anomaly with SU2 weak. But this is just an artifact. It's hidden in a basic rotation because you go to B minus L and B plus L, and you realize that only this linear combination has a mixed anomaly with SU2. And this has, of course, as you know, applications in cosmology, for example, baryogenesis and others. So it turns out that if the symmetries are exact, you can always perform this field redefinition, go to this basis, where only one linear combination of U1s, which I'm calling here U1PQ, has a mixed anomaly with G gut. This is the one that has a non-zero anomaly coefficient, and the rest just have zero anomaly coefficient. They are anomaly-free U1 global symmetries, which of course, if you break spontaneously, they give you Goldstone bosons. But these Goldstone are decoupled from gauge bosons because they have a zero anomaly coefficient. And as I said, then is when quantization becomes important, because the zero remains zero to all energies. Whatever you do to your theory, these Goldstone bosons remain decoupled from gauge bosons, at least via the anomaly. Okay, so the result is that at very low energies, below the electroweak symmetry breaking scale, topology plus gauge invariance of the full gut theory tells you that there is a single axion linear combination, A. This linear combination corresponds to U1PQ. It can be in an extremely complicated linear combination of these symmetries, of these axions. But what matters is that it's just a single linear combination, and this is all that matters for the experiment, because what you find is that the same linear combination that couples to photons necessarily couples to gluons because of gauge invariance. And this tells you that anything else, every other axion, is just decoupled from gauge bosons, and furthermore, this guy is going to get a potential from QCD. So whatever you do to your theory, whatever is the number of axions, the prediction is that in the context of GUTS, this axion A is going to lie on top of the QCD band, meaning that if you find something away from it, this is just incompatible with unification. Okay? Now, this is a strong statement that you can rule out GUTS with finding an axion here in one of these experiments, if you find an axion here. So what we did is also to consider possible loopholes to this statement, to this result, And for this, we consider the effect of axion mixing. We consider the effect of additional axion-like particles like emergent ALPS, pion-like fields, essentially, that could, in principle, couple to gauge bosons. We also consider the effect of dark photons in relation to milli-charge that someone asked before, effects of grand unified theories in extra dimensions. Everything that we find is, or everything that you can get, is on top of the QCD axion, additional axion-like particles to the right of the QCD band. To the right means that they have coupling to mass ratio, which is bounded to be smaller than that of the QCD axion, given parametrically by this quantity. So just to give you a sense of how this works, the simplest example, just two axions coupled to gauge bosons in the context of a GAT. Let's now introduce mass mixing. What we have here is this linear combination A plus B coupled to gauge bosons, and the orthogonal linear combination A minus B is going to be decoupled. But because of this term, this mass term here, both linear combinations are going to mix. And what you get is that, of course, as you can imagine, mass and interactions eigenstates do not coincide, so you have non-trivial effects because of this term. And what this implies is that the additional axion, something like A minus B, also inherits a coupling to photons via the mixing with this linear combination. And where it lies in this plot entirely depends on what is the value of this ratio. When MB over MQCD, where MQCD is the QCD axion mass, is large, you just integrate out this guy. B becomes a very heavy axion-like particle, and it lies well to the right of the QCD line here. Now, if MB is very small, then you get a light axion-like particle, but the coupling of this guy is entirely induced by this mixing. This means that this is mixing suppressed, and the mixing for scalar fields typically goes, or always goes, as m squared over mqcd squared, meaning that you will be somewhere here along these lines. You can also do the brute force approach, which is just scanning in the different parameters FA, FB, and MB. And what you find is whatever are the values for these relevant parameters, you always lie to the right of the QCD axion prediction.
So is your argument sensitive to or insensitive to the presence of kinetic mixing among the axioms?
Yes, it works also for kinetic mixing. You just first go to the canonical basis.
You just diagonalize the kinetic term?
Yeah, you diagonalize the kinetic term, then you will. The linear combination here is probably more complicated, and this one is probably also more complicated, but the argument goes through.
You just screw up the integer nature of coefficient, otherwise you don't.
Yeah.
Makes sense.
And sorry, yes. Can you tune it? Can you just tune the mass by coupling to some other gauge group that gives a contribution to the opposite sign, or the sign is fixed? Because if
So
only one gauge group, the sign is fixed.
You mean something like the total potential is the QCD
plus something else? Yes.
plus something new, where there is there is lambda QCD for minus lambda prime for. So you perfectly tune the offsets of the potentials, and you perfectly tune lambda and lambda prime. So that you can always do. You can always tune things, but even if you do this, which is very tuned, especially if you want to explain cosmic birefringence, then what you also get is a very light axion that couples to gluons, and there are bounds from white dwarfs, from the sun, and all this.
I'm not sure, but I mean, it could be in the region that you say will exclude GATs, but is not yet excluded, right?
So more precisely,
As much as I want, I don't have to tune it to 0.
Yeah. So you could go maybe a couple of orders of magnitude here.
Yeah. Can't you go anywhere, like wherever you want there?
You mean like here?
Well, okay. No. I know that there are bounds where when it's very tuned, but I think there's a few orders of magnitude.
There is, I think there are 3 orders of magnitude until you reach the white dwarf bound, because there is also a bound from neutron stars, which we are talking now, but for context, about the coupling to gluons, not for the coupling to photons. The neutron star bound is closer, but people say is less reliable. You could be in between the QCD line and the white dwarf limit, yes. But that's, yeah, there's nothing I can do against tuning, yeah. Okay, so yeah, that was related to mixing. I was just saying that this is, of course, independent of the number of actions. It's just a property of the coupling being mixing induced for any other axion which is not a QCD axion. So just as a warm-up before going to the string axiverse, there is a kind of a EFT approach to stringy GATs, which is known in the literature as orbifold GATs, proposed and developed in this series of papers 25 years ago, where essentially what you have is a GAT like SU5 in a 5-dimensional theory. Then you compactify the 5th dimension on an orbifold instead of a circle. And because of this, you can always localize defects like branes at the orbifold singularity. And the main motivation for this was, for example, to solve some problem of minimal GATs such as the doublet-triplet splitting, which is essentially just trying to answer this question of why is the Higgs doublet much lighter, or the one we observed in the standard model, much lighter than this representation, which would trigger proton decay. Good. So why do we care in the context of this talk about this kind of theories? Because we would still call them a GAT in some sense, and because for the same reason that I can have incomplete multiplets, I can always have brane localized axions, an axion that lives here in at this orbifold singularity, and because of the boundary conditions, I am free to choose the couplings of this axion to each of the gauge sectors in the standard model in a non-GAT symmetric way. Something that is going to be important is that in every of these theories, the way you compute the effective coupling in the 4D theory at the compactification scale is the following. This is 1 over alpha I is the gauge coupling in the 4D phase for the SU3, SU2 or hypercharge. It has a bulk contribution, which is coming from the GAT symmetric bulk. So the size the size of this contribution is proportional to the extra dimension, plus a localized contribution that comes from degrees of freedom living here at the orbifold singularity. If you want to keep the success of unification, that is why couplings kind of approximately unify here at 10 to the 16 GeV, then what you need to impose is that the bulk contribution is much larger than the localized contribution, and this is going to be crucial when we estimate what is the mass of these brane localized axions. Before going to that, a reminder of how axions can appear in 5-dimensional gauge theories. Let's take a simpler theory than the orbifold GAT. Let's put QCD and an extra U1 in the bulk. As you know very well, we can have this kind of Chern-Simons couplings, which, under some conditions, give you an axion coupled to gauge bosons in the 4D EFT, where the axion comes from the 5th component of this gauge field. As you all know very well, the quality of this axion is typically better than the field theoretic version. This is, for example, nicely explained in Marius' paper. And this is because essentially the shift symmetry is protected by the global one-fourth symmetry, which is typically more robust than a zero-form symmetry and only broken by this kind of non-local effects.
Can I ask something?
Yes.
So, I understand this statement, but I've always been puzzled by the fact that this one-form symmetry can be broken by fermions in the field dimension.
Mm-hmm.
So it seems to me that you're making a strong assumption, which is an assumption in the field content of the
I'm making a strong assumption about not having light particles charged under U1. Yes.
Yeah, exactly.
In 5D, field theory 5D, this is not well justified. In string theory, this is well justified.
Okay, in string theory, maybe if you have a UV completion, which is, full UV completion, maybe in some examples it will be true, in some other examples.
In some other examples may not be true, but for example, whenever people talk about axions coming from, for example, from Ramon fields, you know that the charge state under this field is going to be a D brane, and the D brane has a tension which is related to a string scale up to 1 over G string. So that in that case is well justified.
Also, in this 5D model, in 5D, you don't have chiral forming in the work, right? You can only get a chiral forming by the orbital
It
projection.
doesn't need to be cut.
That doesn't matter.
Oh, yeah, sorry.
Because even if it is vector-like, it's
Sorry, yeah.
in principle a problem.
Yeah.
Because this mass could be much smaller than 1 over r.
That's right. That's right.
So I totally agree, but at least you see the fact that this is not broken by a local operator. Yeah. Good. And by the way, yeah, in this case, it would just make things worse for the QCD axion. So let me just continue here. Good. So orbifold GATS, we have this symmetry in the fifth dimension, plus or times the brain localized or boundary localized theory, which is standard model like. We can have two different kinds of axions, bulk axions like this one I discussed before, and brain localized axions. For the bulk one, I know that the couplings of this guy is going to be GAT symmetric because it couples like this, and G here is the field strength of SU5. So when you dimensionally reduce, then you're going to get something which is like the QCD axion essentially, because it couples to everything that comes from SU5, and therefore you couple to photons as well as to gluons. On the other hand, brain localized axions are free to couple in a non-GAT symmetric way, but still I can assume that they are zero form gauge fields, and in field theory, again coming back to your question, I could introduce local operators to break their shift symmetry, but let me assume that I have a string completion in mind, and this is something like the Ramon-Ramon zero, like the Ramon-Ramon axion or something like that, which still gets only exponentially suppressed potential. Then the matching condition becomes crucial, and this is because, as I said, the 4D EFT, the gauge coupling comes from a bulk contribution plus the localized contribution, and if we want to keep very precise unification like this, then we need to impose this dominance of the bulk contribution, which means that the instanton living on top of the brain, the one that couples to B, has a small action, because when you do an EFT approach, you don't see this, but from a UV completion of the orbifold GAT, you would see that the action of the instanton coupled to B will be given by 2 pi over alpha brain, and 1 over alpha brain is order 1. So what this means is that you are correlating the precision of gauge coupling unification with the mass of the ALP. And it turns out that if you demand that gauge couplings approximately unify, any axion that has non-GAT symmetric couplings living on the brain is going to be heavy. So this is the result for orbifold GATs. Again, very much like in 4D, the coupling to mass ratio for any axion-like particle, be it the QCD axion or a more generic ALP, is bounded above by the QCD axion prediction, and this region to the left, by the way, for context, the thick or the solid black line here is the QCD axion prediction. Any region to the left of this line is not compatible with orbifold GATs where gauge couplings approximately unify.
That's KSVC.
KSV.
Sorry, the line which.
Oh, I'm just assuming that I have a standard embedding of the 3-to-1 of the standard model into the GAT gauge group, so you can, your E over N is 8 over 3.
Okay.
Yeah.
So another way of saying it is there's a low energy QCD contribution to the axial potential, and you might have the small instant contribution of like a 5D SU5, let's say, so they are just suppressed.
5D.
Yeah, am I saying the other way around? Actually,
so the small instanton of SU5, which is a particle around the extra dimension,
Yeah.
is always suppressed by 2 pi over alpha GAT.
That's right. So basically, axial potential is dominated by the localized QCD.
Yes, for the bulk axion. For the brain localized axion, the potential is dominated by the UV instanton, which lives on the brain.
Yes.
But now you have a dynamical criterion to link the instanton action to something like the precision of gauge coupling unification. Okay. So in the last, in the second part of the talk, I promised also to say something about Stringy axions. This is, as I said, a project I did with Pratik and Mick, as well as with Timo more recently. And yeah, I think I don't need to motivate this a lot. I will just say that from a model building perspective, for example, I think one of the attractive features of string theory in some sense is the high degree of uniqueness, where everything is more or less fixed or kind of fixed at the 10D level. We understand how to get something, and let me emphasize the something, like the standard model, at least with respect to representation and gauge symmetries in 5 different corners of the string landscape, and these are related by via dualities. Something which is pretty generic in almost all of them, at least in the geometric regime, is the proliferation of axions in the 4-dimensional EFT. And this is, as I said, as a phenomenologist, something that makes this framework very exciting. Before going to the main results, let me remind you how to get axions from string compactifications. This is just a generalization of the 5D story, where instead of standard gauge fields, we have just higher form fields integrated over cycles in the internal manifold. For example, we have the B field present in all string compactifications, or Ramon fields, which all of them, when we integrate over closed over P cycles in the compact space, we get perturbatively massless Goldstone bosons in the 4D EFT, which, as I said, get only this kind of exponentially suppressed sheaf symmetry breaking potentials. And this action, for example, as also reviewed in this paper by Marius and Nathaniel, typically, at least when cycles are largish, this action, instant-on action, tends to be also large enough in order to solve the quality problem, for example, of the QCD axion. Now, this is not a new topic, of course. Axions in string theories are as old almost as the heterotic string, but I think it's also fair to say that since 15 years ago, more or less, this had an impact also in phenomenology, because these people realized how the complexity of the compact space, at least in those theories where we get something like the standard model, is in one-to-one relation with having many axions at different mass scales that lead to very rich phenomenology. And this is what, in the pheno community at least, is sometimes called the string axiverse. So just for context, I'm going to focus on the heterotic string, but just for context, there is a lot of recent or current efforts by many people, in particular in the type 2B corner, let's say, where, for example, the Cornell group and friends have studied many aspects of the type 2B axiverse numerically, and this is something that, to my mind, is possible thanks to developing codes like this CYTools package, which essentially allows you to extract from this Kreuzer-Skarke database some topological quantities that allow you to build Calabi-Yaus and extract masses and decay constants. And this is, in my opinion, something that has made quantitative studies of the string axiverse possible, and it's very interesting for pheno. I'm going to focus on something else, because I'm not going to need all these numerical tools to get these results. I'm going to focus on the heterotic axiverse. And the reason why I'm going to do this is because in these theories, in the heterotic EA cross E8 SO32 or type 1, which is related by S-duality to this one, I'm going to be able to make statements which are quite well defined, are testable predictions for the axion photon coupling. And this is just going to come from the fact of imposing, as you know very well, anomaly cancellation tells you what is the gauge group, and realizing that this is in one-to-one correspondence with axion couplings. So just a quick reminder of the heterotic string. This is a theory of closed superstrings in 10 dimensions. The effective action is 10D n = 1 supergravity coupled to Young-Mills. And the massless spectrum, as you know, contains the supergravity multiplet, which contains the metric and moduli fields, the B field, which is the most important character for axion physics in this theory, as well as the dilaton, plus the Yang-Mills supermultiplet, from which we get charged matter. As I said, anomaly cancellation, that is the Green-Schwarz mechanism, tells us that the only possible theories have, in 10 dimensions, E8 cross E8 or SO32. I'm going to focus on this one because it's, as you can see, it has two gauge groups, so it's a little bit more complex, let's say, than this one, but anything that I will say for E8 cross E8 will also apply for SO32. Yeah, and the reason why axion couplings pop out in some sense quite naturally is because if you go to the Green-Schwarz counter term, you will find these kind of interactions between the B field and gauge fields, which when you integrate over the compact space, you get axions coupled to gauge bosons in the 4D EFT. Good. So we seem to face a problem here, and is that while the theory in the UV is very simple, only two possible gauge groups, we have many possible four-dimensional EFTs that become available, essentially. And this is because we are compactifying on a six-dimensional space, which we can choose to be a Calabi-Yau, for example, a toroidal orbifold. We also have the freedom to turn on discrete Wilson lines, to turn on U1 fluxes. In this way, many theories, many 4D EFTs become available, from things that look unified to things that look less unified, and even the standard model alone at the compactification scale. So we seem to be in trouble to make sensible or well-defined predictions, but the nice thing of axion couplings is that you can literally match axion couplings from 10D to the 4D EFT at low energies, and this is because you can match the mixed anomalies between the gauge symmetry and the higher form global symmetries at the 10D level to the 4D EFT, where you will be considering the mixed anomaly between the axion shift symmetry and the gauge symmetry that remains in the 4D EFT. So when doing so, what you find is that the results do not depend on any complicated detail at intermediate scales. The result will only depend on how you take the 3-to-1 of the standard model and you embed it into E8 cross E8. That's the only source of model dependence.
And it cannot be that the 3-to-1 comes from the geometry?
In what sense? What do you have in mind?
If you have some KK compactification, you're going to have gauge fields coming from the...
You mean some of these graviphoton, but...
these 6 dimensions is not enough, I don't know.
Yeah, that typically leads to a non-chiral spectrum, n equal to, I think, in 4 dimensions. I don't know if you can get that in this class of compactifications. What you could ask is, so in doing weakly couple, and that's why the weakly couple word becomes important, and just considering out the gauge group which is realized at weak coupling, you could ask what if we have NS5 branes, which are space-time filling, and we put the standard model there. That is not available in weak coupling. That would change the results. And that's why, I'm hopefully also, yes. Here, the word perturbative is important. So the result is that every perturbative heterotic string, also independent of how you break the gauge group and whatever, is going to have the same prediction as in 4D GATS. And so this is the result. And let me now try to explain how we get it. Before going to the details, let me remind you, heterotic axions come, as I said, mainly from the B field. The B field in 10 dimensions has a dual, which is a 6 form, and that's why we have two different kinds of axions. We have the so-called model-independent axion, which is integrating the B6 over the entire compact space. And it's called model-independent because it has properties like couplings and decay constant, which are independent of the compactification. For example, the decay constant is predicted just in terms of the Planck, for the Planck scale and the gauge coupling at the KK scale. And the couplings to gauge bosons can be easily extracted from the modified Bianchi identity. Now, model-dependent axions, they are called model-dependent because even their number depends on the compact space. The decay constant also has a mild dependence on the compactification, but crucially, and this is very important, the couplings to gauge bosons will always come from the Green-Schwarz counterterm. And this is something which is fixed at the 10D level by demanding consistency of the theory, and this is what is going to give you some model independence for the result. I think I have to go faster, but this is to get the coupling to gauge bosons essentially in the 4D EFT. You would start from the 10D Sugra action and you would dimensionally reduce to the 4D theory. Separating the different couplings, we have the model independent axion coupled like this, universally to all the gauge bosons, where, just to remind you, trace 1 F² is just compact notation, and what I mean is all the gauge sectors which are unbroken in the 4D EFT and came from the first D8. The same with trace 2, and what you see is that as you also could deduce from the modified Bianchi identity, A couples universally to everything. I'm omitting trace R² because it's not going to be important for phenomenology, but it would also couple to that. Now, model-dependent axions. They couple like this. Bi is coupled to trace 1 F² as well as trace 2 F². So this is the model, let's call it model-independent prediction for these couplings. The model dependence comes from this parameter, Ki1, Ki2, which are calculable anomaly coefficients which depend on the compact space. They also depend on which fluxes you turn on and all this. But the important point is that Bi couples universally to trace 2 F², trace 1 F² and universally to trace 2 F².
So these KIs are basically product of Green-Schwarz coefficient and the flux you turn on when you
yeah. So you would take this 8 form,
right,
which contains terms like this. Yes. You would integrate over the internal space,
right,
and depending on which fluxes you have,
yes,
which you need to satisfy the Bianchi identity,
okay,
you will get. Oh, this is the thing.
yeah. Okay.
Yeah, and remember this is a 2 form, so you integrate something like this kind of instanton, let me call it, or 4 form over a 4 cycle, and this over a 2 cycle. Yeah. Okay, so the most important part is that at the end of the day, whatever is the linear combination is just two different linear combinations, θ1 and θ2, coupled to trace 1 F² and coupled to trace 2 F². So they can be extremely complicated, but this, from the point of view of phenomenology, from the point of view of the experiment, it doesn't really matter. What matters is that you have θ1 coupled like this to gauge bosons in the 4D EFT, and θ2 coupled to gauge bosons like this. So now, instead of a broad range of possibilities, you only have 2 different options, which is you take the standard model, you embed it into a subgroup of E8, of let's call it the first E8, and the second E8 remains like a hidden sector. This is what I'm going to call the standard embedding. This is the standard approach to phenomenology since the 80s. And the second possibility is just to take the 3-to-1 of the standard model and have a very non-trivial embedding into the 2 E8s. And this is done, for example, in this paper by Timo, Ralph, and collaborators. Oh, sorry. Yeah, so 2 options. Let's do the simplest first. This is just the standard embedding into E8 cross E8 is, as I said, just take the 3-to-1 of the standard model, embed it into the first E8, and leave the second E8 as a hidden sector. In this case, from the pheno point of view, you just care about θ1 because this is just going to be, θ2 is just going to be gravitationally coupled to us, and because the standard model lives here, not here. So let me call this θ1 the visible quote quote axion. As you see, θ1 can be a very complicated linear combination, but the point again is that from the point of view of the experiment, this is just a single linear combination. It looks very much like a 4D gut, meaning that if the standard model comes from this first E8 only, in a way which is completely independent of the compact space or which theory you had at the 4D at the KK scale, then you know that finding an axion above the QCD line is incompatible with the heterotic string with this kind of embedding. Of course, as before, whenever you have additional axions that get a coupling to photons via mixing with theta 1, this region can be populated by additional axion-like particles, but I want to emphasize that this region is just incompatible with the heterotic string. Okay, so the second option, as I said, is a non-standard embedding of the standard model into both E8s, and this is not the standard, let me call it non-standard approach, because it's really hard to obtain phenomenologically allowed theories. As far as I know, only this paper has considered this kind of embeddings in the past. And the idea is that you take the QCD and SU2 of the standard model, you put it into the first E8. So this guy becomes the QCD axion. And now you take hypercharge, for example, and you have a non-trivial embedding into both E8s. That is into U1 factors in both E8s. Now, morally, electromagnetism also lives in the second E8. So you could ask if this theta 2 is now a light axion-like particle. This is, as I said, non-trivial because there are three conditions that have to be matched. The first one is that you want to avoid any confining sector from the second E8, because otherwise this would make theta 2 very heavy. Of course, if it is very heavy, then we are done, because we will be again in this situation where theta 2 lives here and theta 1 lives on top of the QCD axion. I'm just trying to see what is the least trivial option that we can have. So second condition is that we need to avoid all kind of chiral fermions coming from the gauge genus in the second E8 that could have a standard model charge, because remember that electromagnetism lives here, because if this is the case, you will have chiral exotica, which is excluded experimentally, for example, from LHC. Finally, we need to make sure that at the weak scale, we reproduce the right value for the gauge couplings, like the strong coupling of QCD is very well measured. The weak mixing angle is also very well measured. And since we have a non-trivial embedding of the gauge symmetry of the standard model into both E8s, this is a non-trivial requirement. So I don't have time for lots of details, but you can take my word, you can go to this paper with Timo. There are non-trivial models using something called line bundle breaking, which is nothing but turning on fluxes, where you can reduce the second E8 down to U1s only, so there is no confining interaction, and you can obtain hypercharge as a linear combination of U1 factors here and U1 factors here. This is possible. The problem and the condition which is less trivial is this matching condition. Remember, I want to obtain the right value for the sine square for the weak mixing angle, and I'm placing hypercharge into both E8s. So there is a non-trivial matching condition that tells me what is the gauge coupling of hypercharge in the 4D EFT, and it receives contributions from the first E8, a standard contribution, and from the second E8. Now, if you only had these two contributions, then you would be ruled out, because we want to recover the gauge coupling at low energies and we wouldn't be able. But line bundle models also introduce this kind of holomorphic threshold corrections, which I'm calling here delta. So I'm just going to assume that for some reason the threshold correction conspires to kill this contribution and you can get the right value of the gauge coupling. Because I want to be challenging this result as much as possible, so let's see what we can achieve. Okay, so we satisfy then the three conditions: no confining interaction, no chiral fermion, and the right values for the gauge couplings. So now we just need to compute what is the mass for the axion theta 2. And in this case, there is always an irreducible mass that will come from UV instantons of the second E8. And we can estimate what is the axion potential for theta 2 coming from these effects. When you do the algebra, you realize that in addition to the 3-level contribution, there are also contributions which come from one-loop holomorphic threshold corrections. And at the end of the day, if you impose gauge coupling unification plus perturbativity, that's why I said that the word perturbative heterotic string is important, what you find is that this action is also order 1. So theta 1 is an ALP, it avoids the coupling to gluons, but the moment you impose these two conditions, then the mass of theta 2, which I'm calling here M ALP, is large, and therefore the coupling to mass ratio will be small. More quantitatively, this is a very busy plot, but the idea is very easy. I'm assuming here that the one loop threshold correction is smaller than just a random value, 75% of the 3-level contribution to see how this goes. And what you find is that the red region here is not allowed in this kind of non-standard embedding into both E8s. So even if the one loop threshold correction is quite large, there is no axion-like particle to the left of this in this red region essentially. If the correction was smaller, let's say 50%, then this red region would completely collapse to the QCD axion prediction. So just to finish very quickly, what we are doing now, we are trying to also study this kind of results in the context of F-theory GATs, which are more similar to D-brain constructions, and there the non-trivial bit comes from something called hypercharge flux breaking. Hypercharge flux is very simple to understand. You turn on a flux for hypercharge, and the initial gauge group, which could be SU5, breaks to the commutant of the that is to the subgroup of SU5 which commutes with the hypercharge. And this is by definition almost in SU5 the 3-to-1 of the standard model. So the reason why I say this is non-trivial in this case is because turning on this flux also introduces holomorphic threshold corrections which are known to modify the gauge kinetic function in a non-universal way. So you would start with something that is perfectly unified and has a single axion coupled to gauge bosons and is the QCD axion, but because of this effect, you will not only change the gauge couplings at the KK scale non-universally, but you will also induce axion-like particles which couple to photons without coupling to gluons, because these corrections are holomorphic. Now, very much as before, or very much as in the case of orbifold GATs, you can estimate what is the ALP potential. It's again something like this, schematically, and what we are finding, the goal, is to show that the instanton action that breaks the shift symmetry of the ALP can be connected to the gauge or to the precision of gauge coupling unification, in the sense that, again, when gauge couplings approximately unify at the KK scale, this instanton action is small. Hence, this potential is very relevant, and B ALP is very heavy, because then this is what gives you the power to come back to a situation like this. Yeah, so just to finish, I think this is the summary or the 3 main things that we can learn from this talk, which is, I think it's fair to say that in addition to the usual questions like solving or not the strong CP problem or the dark matter puzzle, I think the fact that axions can give us very valuable information about the far UV is just making axions more attractive in phenomenologically and for the experiment. I just gave you a few examples about in the context of unification. There are many others, as you know very well, from domain walls to the global structure of the standard model and all this. Second, I think I want to emphasize that as a phenomenologist, what makes this very interesting is the huge experimental program trying to find this particle, which is truly remarkable. In the near future, this is another plot, which is probably a little bit optimistic right now, but that is the idea, more or less, that there are going to be new searches trying to find the axion in new parameter space. Most of this parameter space is where the coupling to mass ratio is larger than the QCD axion prediction. So this is the region where we can test all these theories. And finally, I also want to emphasize that I don't want to claim or say that we can confirm these kind of theories by finding an axion. I think we cannot, for the same reason that finding proton decay does not confirm a gut, in a sense. But I think it's remarkable that axion searches at least offer very non-trivial tests of these theories. Thank you.
Questions?
Yeah, thanks for the great talk. I have a question which I feel like maybe related to Rafael's earlier comment, but here's my question. Suppose you started out with your UVB, either God or some version of the string theory. To be concrete, let's just take a God. So then we as a UV boundary condition, when God group is broken, you have this effective action theory, and if we just have the data, you have to be on the right side of this QCD line. That's your claim, right? Then suppose there is an extra information, extra stuff inside of the God, such that as I RG flew, somehow it has either KSVZ or KFZ or whatever type of a module inside, which in other words there has been a U of global symmetry extra. It's not been spontaneously broken as yet. And then it produces extra axion in such a way that it can also couple to at least a part of the same amount gauge group. So then you have to sort of reorganize what you might call axion. Now under this, in order to avoid your constraint, I guess we still need to invoke somewhat miraculous cancellation to move to the left. Would that be your perspective of this possibility?
So what I think so what you're saying is what happens if there is an axion that comes from a generator which does not commute with the standard model, with the gut gauge group.
Yeah.
Right? Because one of my assumptions, which I probably did not make very explicit, was that the global symmetries that I was considering was these kind of global symmetries which are U1s and commute with G gut. Good. So first of all, if we will only have this kind of mixed anomaly if the symmetry is U1. So that's why I only cared about these ones. And I did not consider explicitly cases where the axion comes from a generator which does not commute with G gut, because those actions will get a perturbative mass.
Right.
So this is very much like the charged pions. The classic example is the charged pions getting a mass from electromagnetism, because the generators do not commute with electromagnetism. So if you have a axion that comes from a generator which does not commute with gut gauge bosons, you will just have this kind of perturbative masses.
Yeah, in other words, whatever extra action I was having in mind should come from accidental U1 symmetry emergence.
Yes, but the point is that the gauge symmetry always breaks that
right.
explicitly.
Okay.
And that is really hard to...
But also, they also keep the dead axion probably to the right also, because just give them
Yes, yeah. We have an example of that. So if the axion was a fundamental field, this is just similar to the hierarchy problem, the axion will be super heavy. If the axion was a composite field, I have a huge backup, but I think it's somewhere here.
Right.
I think is, yeah, this thing. Yes, this is the pion case. So good. So imagine we have some compositeness, some composite sector, and we have some flavor symmetry. We have pion-like fields that emerge below the chiral symmetry breaking, and there will be a guy. I'm gonna skip the detail. There's one guy here living in the adjoint of SU5 that has the quantum numbers of the hypercharge generator. This is something like what you had in mind. This is a Goldstone, pseudo-Goldstone boson that will couple only to photons without coupling to QCD. When you account for the breaking from this kind of perturbative breaking from heavy gauge bosons, you induce this kind of dimension 6 operator. This generates a mass for this ALP, and even though this gut scale is huge, the fact that you can use here constraints, experimental constraints, to bound from below the decay constant, tell you that the ALP mass in this case is larger than 1 GeV.
But crucially, probably.
It's way to the right. I mean, we are talking about GeVs here.
Yes, yes,
so
yes. Right.
it's even,
Okay.
the QCD axion line would be somewhere here.
Okay.
I think so.
Thanks.
Yeah, I have some questions. I didn't understand something, which is whether the fact that in all of your models, everything was to the right of this QCD axion line, if it was from pure consistency or just trying to reproduce non-phenomenology and maybe gauge coupling unification.
If you give up gauge coupling unification, then you can have whatever.
Okay, so this would then, I could interpret these searches as tests of unification.
Yeah. So the moment we decided to go to orbifold GATS, it's like a little bit similar to the discussion this morning. The moment we decided to go to orbifold GATS, and we take a brane and we place it at the orbifold singularity, we are already giving up many things about standard GATS, 4D GATS, because I could have, nothing stops you from having a fermion localized on the brane, which has 1/2 electric charge. That's why you can solve the, the doublet triplet splitting problem, because you can have, for example, incomplete multiplets. Now, you could insist like, okay, we give up that, but we still want to keep the successful prediction of gauge coupling unification, and we kind of call this GAT. If you also give up this, then you can have axion-like particles, but I also wouldn't call that a unified theory anymore.
And my second question was, it seems to me that many of these couplings that you were studying, they came from the quote unquote topological couplings in Sugura, right?
Yes, all of them. Yeah.
Right. So so people have various Calabria or whatever, like SUSY compactification under control, but does it actually depend on, imagine someone was doing model building, like non-supersymmetric compactification, if they could control, no one knows how to compute anything, right?
Mm-hmm.
The question is, does this depend on which string theorem looking at, or does this compactification is supersymmetric, or can I do anything I like?
So here, and just considering this kind of n=1 in 10D, I think for the non-supersymmetric you can have this SO16 cross SO16.
But this
is morally the same almost.
Take the 10D SUSY string theory,
compactify
it on a 6-dimensional manifold that breaks all supersymmetry, right? It seems to me that all of these things are generic. It doesn't, even though
I think the moment you start with this, and the moment actions come from integrating B over 2 cycles or the 10D dual over the entire space, breaking supersymmetry does not modify this. Breaking supersymmetry typically what does is more related to the dynamical aspects of the theory, like axion masses and axion decay constants. But the quantized part, I would say, is unchanged. Yeah, I'm not 100% sure, but that would be.
So rule gauge unification. If you break SUSY at very high scale, should it rule gauge unification?
Do you?
You do.
Well, but you don't know if there are. I mean, you ruin the success of MSSM unification, but you don't know how much of other stuff you're getting from here.
Saying if you break SUSY literally at the gas scale.
Yeah, because you have in mind MSSM-like particle content, but I have no idea what this is going to give me. And also, like, you ruin it. There is a 10% here, which there are threshold corrections and all this, which have to be taken into account. I'm not claiming that is the, yeah. I would say that does not really depend on SUSY. Yeah.
Okay, last question of the workshop. Okay, now let's thank
Mario again.
Thank you.